Hello, welcome to another Stat 432 video. In this video, we're going to talk about cross-validation. I do want to say it's going to be the first time we talk about cross-validation, so we're going to stick to the very basic structure of it, and I'm going to sort of try to, in one video, do it both on a whiteboard and in R to drive the main idea home, but know that this is not going to be our last time talking about cross-validation. We're just introducing the main idea, which is very related to resampling, which we've already seen through the bootstrap. But this is something that's going to be more directly applicable to sort of the machine learning process that we've been going over. Although bootstrap will also reappear later, but in the context of a model, not in the larger process. But that won't make sense yet. So first we need to talk about cross-validation. Okay, so this schematic here sort of outlines the procedure that we've been doing up to this point. So we take our data, we split it into a training data set, and then a test data set. And then within the training data set, we split it off into an estimation data set and a validation data set. And this estimation data set is perhaps a bit confusing to folks because other resources might call that the train data set. But then my question is, well, what do you call the data set that I have here labeled train? And the reason for this is going to be somewhat clearer in this video. But basically, what have we been doing, right? So with the estimation data, that's sort of our step one where we fit our models. So we fit a bunch of models here, and models could be, say a bunch of models of the same, using the same algorithm with different tuning parameters, or just a bunch of different models. But ultimately, what we do once we fit all these models is we evaluate how well they're working with the validation data. Okay. And then based on that, we select a model. So far, we've just been saying, hey, whichever model gets us the lowest error or the best metric in the validation data, that's the model that we're going to use. And then that we fit to what we call the whole training data. So we say fit the chosen model. And then the purpose of the test set was to say, okay, now that we've selected our model, how well does it work? So here is step 4 in our procedure. We would say report performance of chosen model. Okay, and we've done this procedure over and over again. But there's kind of an issue here. Perhaps this has been eating at you and you've been wondering, like, why are we doing something that has this obvious problem? But the problem is right here. So if we're taking 80% of the data and making it the estimation data, and 20% of the data and making it the validation data, well, our results then are sort of highly dependent on which observations end up in the validation data, or vice versa. So ultimately, this procedure is too variable. Basically, it's too sensitive to the data split. So even if we ignore the fact that we first train test split the data, just the estimation validation split itself is adding a bunch of variance to this procedure, where what we'll see when we get to R is that we might select wildly different models depending on just the randomness of the split of the data. So what we want to do is reduce that variability. Okay. So before we sort of talk about this in the context of machine learning models, I want to mention sort of one of the most classic results in all of statistics. So suppose we had this setup where we had x1 through xn, which are IID random variables with mean mu and variance sigma squared. Often then, a statistic that we look at is the sample mean. And you've probably seen this a million times before. If not, I would suggest now is the time that you commit this to memory. The expected value of the sample mean is the true mean, and the variance of the sample mean is the original variance divided by n. And we like this divided by n quite a lot because in this case, we would say that the average of the observations is much less variable than any individual observation. Well, that's interesting. So we're going to try to use this idea here. So one thing you could sort of imagine is, okay, well, let's just say we test train split the data already. Instead of doing the estimation validation split once, and then so say you have a model that you want to fit, you estimation validation split, fit the model, make predictions, calculate your metric, call it root mean squared error, right? Well, then just repeat that process a bunch of times. So a new random split, fit your model, get the predictions, calculate the root mean squared error, and do it over and over and over and over and over again, and then average the results. And in some sense, that's what we're going to do, but we're going to do it in a specific way that's going to sort of limit the computation, and it'll give an answer to, well, how many times do we do this? And it's going to be not that many. Okay, so enter something we called k-fold cross-validation. So in this picture, I have a training data set and a test data set. And so the full data set would be 8 observations, 6 of which I have randomly sampled into the training data, 2 of which I have randomly sampled into the test data. So in this slide, I'm only going to be talking about what's happening within the training data. But I just want to remind you that that test data exists. So just keep that in mind. But we're not going to be using it here. Okay. So what I want to do is, in this sort of schematic, I'm going to do what I'm going to call threefold cross-validation. No one actually does threefold cross-validation, but it's just one less. I only have to write down 3 things to do it. So I'm going to call this fold 1. I'm going to call this fold 2. And I'm going to call this fold 3. And I have this ... here to indicate that you could have more and more folds, but I just want to illustrate the process. So the way these folds are generated is they are specific splits of the data within the training data set. So in fold 1, what's going to happen is these first 2 observations are going to make up the validation data, and these 2 observations, 4 and 6, and these 2 observations, 2 and 8, together will be the estimation data. Okay. In fold 2, observations 4 and 6 become the validation data, and everything else is the estimation data. And in fold 3, the last 2, that is observations 2 and 8, become the validation data, and everything else is the estimation data. So basically, in this idea where we're going to repeat the estimation validation split, we're going to do it in a way where every observation has its turn in the validation set. So then what do? Well, for each fold, we fit a model to the estimation data set. We make predictions on the validation data set, and then you calculate your metric of choice, be it RMSE, accuracy, or misclassification, a classification problem, whatever that may be. And then you repeat that process for each fold. So in the next fold, you fit the model to the new estimation data and make predictions on the new validation data, and so on and so forth. So it's just repeating the process over and over again, but making sure that all of the observations were at one point in a validation data set. So where that idea comes into play is that if we say here that metric sub I is the value of whatever metric you're interested in for fold I. And K here is the number of folds. And K is now an overloaded term because sometimes it's number of folds, sometimes it's number of neighbors and K nearest neighbors, but hopefully from context that'll be clear. And again, metric could be whatever you want, right? So in a regression problem maybe it's mean squared error, maybe it's mean absolute error, maybe it's accuracy in a classification problem, whatever you're interested in. But basically, you calculate that metric on each fold, and then divide how many folds there are, and that's what we'll call our cross-validated metric. Okay, great. And that will be a more stable way to select a model. So if we go with the lowest cross-validated metric instead of just what we've done previously, we won't have so much variability in what model we end up selecting. And we can actually get a sort of a hacked together estimate of the variability here. So if what we do is we take the sample standard deviation of what I call the fold metrics, well, this will sort of serve as sort of a standard error of this statistic that we're calculating. And with this, we can add something even more to our selection procedure. Okay, so there's something called the one standard error rule. But first, let's just think of what we would normally do, right? So what I have here is on the x-axis, we have model flexibility. So 1 being least flexible. Or no, let's say this is... sorry, I just have to decide how I want to draw this picture. No, that's okay. I'm just realizing in my notes I have this backwards, so I have to change it before I post it. But anyway, okay, so what we have here is model flexibility. So 1 being least flexible, 100 being most flexible. So this is just some arbitrary flexibility metric. You know what? No, scrap that. That's too confusing. Let's say this is K in K nearest neighbors. So this is the most flexible, and this is the least. Just so there's no confusion, or my attempt at less confusion. So if we did this thing called cross-validation now, and for a bunch of different values of K, we got a cross-validated, let's say, misclassification error, you would say, okay, well, pick the model with this value of K here. And that's totally reasonable. But there's another approach. So if for each value of K, and oh gosh, this is number of neighbors, by the way. Since we're also dealing with K-fold cross-validation. So we could add sort of error bars around each of our cross-validated metrics. So let's say that looks something like this. Okay, so this procedure called the 1SE rule, what it says is, okay, first find the model with the lowest cross-validated error, which is here. Then look at its results plus a standard error, or minus a standard error if you're looking at something more like a max, or a metric that needed to find the max. But so in this case, we're looking for a minimum here. So we want the metric plus a standard error, and then go like this. So what we want to find is a model that is less flexible, but within that one standard error. So this right here achieves that. So that's a model that, in some sense, I mean, this is not, we're not doing a hypothesis test, we're not doing anything technical here, but in a way, we could say that, well, this result here is not significantly different than what we had at the lowest, but it has the benefit of being a less flexible model. so it's less likely to overfit. So this would be just a more conservative approach to selecting a model. Some people really like this, but most often you will find people simply going with the model that achieves the lowest cross-validated error. But I just want to put this out there as we often say find the best model, but some people would argue the best model is a less flexible model that doesn't have significantly different results. Okay, so one more question I wanted to answer real quick is, now shifting back to k-fold cross-validation, which value of k should you use? I mean, you could do anything. I mean, in some sense, what we had been doing all along was one-fold cross-validation, but you could do anything from 2, 3, 4 to however much data you have is how many folds you could do. So there are basically 3 very popular choices. So 5-fold cross-validation, 10-fold cross-validation, and something that we'll call, this here is what we call leave one out cross-validation. So if you select the number of folds equal to the amount of training data you have, that means each observation is going to be its own validation set throughout the folds. So basically, you're doing a one at a time, leaving an observation out, and that's where leave one out comes from. So this is a bit of opinion here, but I would say the 2 most popular choices are k is 5 and k is 10. But within those 2, you'll find probably k is 5 is even more popular, and that's because it involves less computation. Because we're literally taking a procedure we had done before and doing it either 5 times or 10 times. So the more and more you do it, the more computation and the longer things take, and sometimes that's a problem. So k equal the folds equal to 5 is probably what we're going to use most often here. As you increase the number of folds, there are some desirable properties, but for most practical applications, people will just use 5. But 10 would also be completely reasonable and still often computationally feasible. So leave one out. I mean, this will seem like the worst possibility computationally, so it's often not used. But there are some models, for example, a linear model, where there's kind of this shortcut where you can actually calculate leave one out cross-validation by only fitting one model. I'll leave it as an exercise to the viewer to go find a reference to how to do that, but we're sort of not going into the depths of linear models in this course, so we're more interested in using cross-validation in this specific result, but that is something to perhaps keep in mind. Okay, but so all this is sort of conceptual at the moment, so what I want to do is actually do this in R. Okay, so I'm going to go maybe painstakingly slow today, and I have my notes that I'm going to rely on here, but I'm going to type everything from scratch today. Okay, so let's do it. So we want to do cross-validation. So the first thing I need is some data, and I want to do 2 examples. I want to do a regression example where I simulate the data, and then a classification example where I use real data. So I'm going to write a function to simulate some data. Okay, so I'm going to call this generate sim data, and it's going to be a function of some sample size of my choosing. So the x values will be random uniforms where we want the sample size, and for some reason I decided to have a minimum of -1 and a maximum of 1. Okay, and then y is going to be some function of the x's, of course. So what I'm going to do here is a random normal. N is going to be the sample size. The mean is going to be a function of this x here, and in particular, I'm going to cube it, and then there's going to be some noise around that by something like this, and then I'm going to return this as a tibble. Tibble x comma y. Okay, let's check that I wrote a legitimate function. Okay, that looks good. Some very simple data here. We have a numeric y, a numeric x. We want to predict y from x. Okay, cool. So now let's actually simulate data. And I'm going to set a seed here. Okay, so this is the... I should probably do something like this. Okay. So this is the data we're going to use for this example. So what I want to do is I want to fit k nearest neighbors to this data. I'm realizing that I'm going to want to move myself down here. Okay, something like that. Okay, great. So my goal, let's state this. Goal is to fit k. I want to tune k nearest neighbor. So I want to find a good value of k. Like that's going to be our job here. Okay. So we're going to start with our usual procedure, which was first we're going to train, test, split data. Okay, so I think in every other video I've done and everything we've done up to this point in this class, I've glossed over the splitting of data and just did it for you. But now it's going to become kind of important to what we're about to do, so I'm going to walk through this. Okay, so the first thing we need is to know the size of our data. In particular, the number of observations. So there's 500. Okay, so note if I use this sample function here, what this does is it effectively shuffles the numbers from 1 to 500. Okay, but I don't want that many. What I want is only, let's say, 80% of that. And we'll do something like this. A little bit of repeating, but I'm okay with that. Okay, so this is the numbers 1 through 500 shuffled, but only 80% of them. So what I'm going to call this is I'm going to call this the train index. So what this is going to be is these are the rows we want to be in the training data set. So the way we accomplish that then is something like this. So via subsetting syntax, if I run this, what this is now is those 400 rows that we got the indexes for here. And so I'm going to call this the training data. And then for the testing data, we do the same thing, except we do sort of a negative subsetting like this. So notice, I didn't store the training data. But so notice the training data is 400 observations. The test data is 100 observations. Together, these two things make up the original data. A reminder to myself to go run this from top to bottom so I catch this seed. Otherwise, the results will be slightly different, but that's okay. Okay. So next thing we want to do is what I call the estimation validation split. Okay, so this is roughly going to be the same process, except now instead of splitting from within the original data, we're going to split within the training data. So anywhere we have train here, it's now going to be estimation. Anywhere we have validation, test is going to be validation. So this goes here, and then lastly, we're splitting up the training data. Okay, so by my math, if I do this, okay, so the estimation data is 320 observations, which is 80% of 400, and the validation data is 80 observations, which is 20% of 400, and 320 plus 80 equals 400, so something we've done has worked correctly. Okay, great. And like I said, I'm going to run this from top to bottom. Okay. So now I want to go about the business of finding a good k-nearest neighbors model. Okay. So I'm going to go ahead and we'll add a coding lesson here. So ultimately, we know what I need to do is I need to repeat a procedure. The first thing in the procedure is going to be to fit, let's do this. Oops. I can't type today. KNN reg. So Y is the response, X is the predictor, the data is going to be the estimation data, and K is going to be, let's say, 10. Now, I know I'm going to repeat the procedure for a bunch of different Ks, but first I want to make sure I can fit a model, make predictions, and calculate, let's say, RMSE in this example. Okay, great. So did that. Let's check it. Sure, looks good enough. Let's say predict with that model on the validation data. Oh, val. Okay, that seems reasonable. So we'll call this predictions. And then what I want to do is calculate a root mean squared error. So we'll do the predictions minus the actual values, which I believe are these. We will, let's see, square those. We will average them, and then we will square root them. Okay, and that seems reasonable. I'm just going to go back and comment what we did because we're developing a procedure. So here we are fitting a model. Here we are making predictions. And here we are calculating a metric, in this case RMSE, but that could be any metric of your choosing. Okay, great. So now what we need to do is systematize this. So instead of doing it for one value of k, so let's say values of k to try. So I'm going to create a vector here, and I want to try all the k values from 1 to 100. Do you really need to try all these values in practice? Probably not, but I want to show that it's easy to do a lot at once. In practice, you might maybe try every 5 or something. Okay, great. So basically what I want to do is I want to repeat this procedure, except with 1, and then 2, and then 3. So I'm going to write a function. Function to validate model. So I'm going to call this validate model, and it's going to be a function of a potential value of k. So I should say validate KNN model. But I should say that this is still going to be a specific function to exactly what we're doing here, but it's generic enough that I can do what I need to do in this problem. Okay, but I'm saying don't reuse this function. You're going to have to write one for your case. So what I'm going to do is exactly these 3 steps. I'm going to fit a model, but instead of 10, we're going to pass a value of k. We're going to then make predictions. We're then going to calculate root mean squared error. So now that I wrote my function, the first thing I should do is that I should check that it works for the value that I did previously. Okay, so with k is 10, I get this value here, which looks, wait, where did I do it? Aha, here. It's the same value. Okay, so it's working. So now I want to repeat this. So this is a job for, well, I always just do lapply because I'm not particularly smart and I never remember what's going on. So we want to apply to this list this function, and when we do that, we get something like that, but that's a list and I want a vector, so we move to sapply. Okay, there we go. There are a bunch of different, so what do we have here? Let's store this first, actually. So I'll call this validation results. Let's actually plot those real quick. Something like this. Gotta get rid of, oh, not that. Sorry. Gotta move my, oh no. Okay, there we go. So that's not a particularly pretty picture, but that's fine for now. Maybe let's do this instead. And I like a grid. Okay, so this shows us what happens to the validation root mean squared error as a function of k. And so in particular, we want to know where this is smallest. And I don't think I have to worry about ties here, so I'm going to be a little bit lazy and say which dot min of the validation results. Okay, so a k equal to 24 gives us the smallest validation root mean squared error. So that's the model that we would go back and fit to the whole training data set and then evaluate how it's doing on test, and that would be our final model. Okay, that's cool. What happens if I repeat this a bunch of times? So here we selected k is 24, but what if I highlighted my code starting here? I actually could get rid of some of it, but I'm not going to. So what I'm going to do is, without setting a seed, I'm going to just get new estimation validation splits and figure out which model we would select. Here we go. Oh, this time k is 15. This time k is 10. This time k is 32, 13, 30. This seems like a pretty big range of different values to be selecting, just dependent on a random split. Now, that's not super desirable. Now, I should say that while it's not desirable, I think in this case it ultimately won't affect the results that much. But we're at 7, 31. It's all over the place. And you can sort of even see the curve that we're creating is sort of wildly different depending on the scenario. So this is what we want to fix. Even though it's probably not going to affect our result too much in this case, we'd, if nothing else, want a procedure that's for selecting a model that's less variable. So let's do that. Let's now cross-validate this. So in thinking about cross-validation, we're going to have to redo this a bunch of times. And we want to redo it in a way where the validation sets for the different folds taken together would make up the whole data set. So what we're going to do is we're going to use a very handy function from the caret package called create folds. And so I need to give it two things. I need to give it the response variable in the data set that we're going to be doing cross-validation within, which is the training data set, and then a number of folds. And I'm going to say we're going to do 5-fold cross-validation here. So let's look at what that gives me. So this gives me a list where each element is a vector and they're labeled with these fold names. I should actually probably store this, and I'm realizing that's going to change the randomization, but I'm not worried about it. I'm going to call this the index for the folds. And if we look at this, so what I'm going to do is I'm going to unlist this. So what that did is it just smashed all the vectors together. I'm going to get rid of those names because they're a combination of wrong and confusing. And then I'm going to sort this. Well, hey, look at that. It's the numbers 1 through 400. So what these are is these can be used then as indexes for the validation data in the first fold. These would be the indexes for the validation data in the second fold, and so on and so forth. That would be, no, did I not? Hold on just a second. So that would be, if we look at this sort of schematic here, it's the first vector there corresponds to these indexes here, like 3 and 5. The second one would be like 4 and 6, and the last one would be like 2 and 8, something like that. Okay, except we're doing it within train, so we wouldn't have had the missing numbers. Okay, anyway. Okay, so now what I want to do is I want to sort of do this once. So now this will sort of determine validation sets. So if we think about that, if we want to make an estimation data set now, what we do is let's do this for the first fold. So the estimation data would be the negative subsetting, and the validation data would be the positive subsetting. So if we look at these things real quick, so the estimation data is 320, and the validation data is 80 things. Okay, that's good. So then we just do the thing we've always been doing, which I'll even do this. Okay, so what do? We fit a model. Say if we were doing K is 10 here. Then we make predictions. Then we calculate RMSE. So what this would be, so this is the root mean squared error for the first fold. Okay, but obviously I need to do this thing multiple times. So let's write a function. So let's call this function calculate RMSE KNN single fold. A ridiculous name, but it tells us exactly what we're doing. So we need to be able to input at least two things to this. Technically, we should probably be passing the data for scoping reasons, but we're going to be a little bit lazy. But ultimately, what we're going to do is we're going to pass in indexes for the validation data and then a value of k. Okay, so if I steal my own code here and put it inside of the function now, so now this will look like this. So when we fit the model, it'll be to the estimation data, except now it's going to be an arbitrary k. And then, or no, hold on. I want to leave all this. So fit model, split within fold. Okay. That's good. That's good. That's good. Oh, hey, not much changes. Okay, great. So what I want to do is I want to pass the first fold to this function, and let's say do k is 10. Again, that k is for k nearest neighbors. We're doing 5-fold cross-validation. Confusing, but hopefully context will tell you what's going on there. Okay, so there is that number again. Cool. But we need to repeat this, right? For each of the folds. So if I put 2 here, 3 there, 4 there, 5 there. Okay, cool. So there are the root mean squared errors for each of the folds. But surely you're shouting at your computer screen right now saying, Dave, don't repeat yourself like that. That's silly. Of course you're right. So what we need to do is apply our function, which is this, over this list. And we also need to tell it, let's say do k is 10. Much better, right? Here's our RMSE for fold 1. Here's our RMSE for fold 2, and so on and so forth. Maybe I'll even store these things. I will call it, what did I call it in my notes? I guess I didn't. I'll call this CV results. Actually, I don't want to store this. But to say that to calculate then our cross-validated root mean squared error, we would simply take the mean of these things, and there it is. Cool. Okay, so what do I need to do now? Well, now we need to repeat this process for values of k from 1 to 100. Okay, so I need to write a function. So effectively, well, just to show you what we'd be doing. So this is kind of what we're after, right? Except for numbers from 1 to 100. Okay, so let's call this calc CV RMSE for a value of k, which is a function of k. Actually, no. What I'm going to do is this. I'm going to be a little bit fancy. Hopefully this won't make it too confusing. I'm going to call this fold RMSE. Okay. And this should be K. So I'm going to output two things, actually. First, I'm going to output the mean of those things. So I'm going to call this, let's call this CV RMSE. But I'm also going to calculate something else. I'm going to do the standard deviation of that. And we'll see why in a second. But let's see if this worked. Okay, so I'm going to call this CV RMSE results, and it'll be if I s-apply over that vector we saw before of the potential k values, this function here. Will this work? Let's find out. Argument 3 is empty. Aha! One too many commas in this vector I'm trying to return. Anyway, let's try that again. Okay. CV RMSE results. Oh, this looks nice. So what do we have here? So actually, let's massage these results a little bit. I think if I transpose them, that will start to make it look nicer. And then I want to make it a tibble just so we can look at it easier. Ooh, I actually hate that because of the names. Let's just look at this. Okay. So what we have in the first column is the cross-validated root mean squared error for each potential value of k. What we have in this second column is the standard deviation. So for the 5 numbers that went into calculating this, here we looked at the mean of those. Here we're looking at the standard deviation of them. So it tells us a little bit about the variability in this statistic here. Okay. So if I go back to the way it originally was, if I subset like this, those are the cross-validated errors. And if I do which.min 33. So what I could do is something like this. I could redo this a bunch, and then run our functions, and then figure out which one it returns. I'm going to regret this because it's going to take a while. But notice the results we're getting, they're still variable, but they're kind of locked into a tighter band of possible k values. So if we keep redoing the 5-fold cross-validation, it varies, but ultimately we're selecting something that seems to be in that right around 30 range. So we've done what we set out to do, which is sort of make this less variable. Okay, but let's take one of these results for whatever randomization we just had there, and I want to do a little plotting real quick. So what I want to do is I want to plot the k values as the x value, and the y value is going to be the cross-validated results. I'm going to do type equals L. Okay. So pardon me as I do some plotting here. Okay, that looks nice. So what I want to do is I want to add error bars to this. So if I do something like this, and what I'm going to do is I'm going to do, this is not going to be the prettiest code, but it should get the job done. So that's going to be minus a standard error, and this is going to be plus a standard error. And let's give those a different color. Everyone's favorite Dodger blue. Something like that. Okay. Let's plot this. Need to adjust my axes a little bit, so let's do something like this. I think I can get away with this. Okay, cool. So remember that we selected, oh, I don't know. Was it, well, let's check real quick. Oops. 30. Okay. So why don't we just actually, why don't we add that? Add blind v equals 30. Let's make that I need an equal sign. Okay. So where this is the smallest is if we selected k equals 30. But what if I did something like this? Let's do AB line. Then when I want to add, this is not going to be the best code in the world. So what did we say? It was 30. That's hard coded. I should really just do this, but it would make the code too hard to read. And color is dark orange. Did I spell that right? We'll find out. Okay, so now when we plot this, so what I've done is I've taken the value for the cross-validated root mean squared error for our chosen model plus the standard error, and then I've drawn a line. And that means that this model right here, with like a k of like 62, 63, could be an interesting choice because it has a cross-validated root mean squared error that is within one standard error of the one we found, but with a much less flexible model, so there's much less chance that we overfit. So that would be using what we call the one standard error rule. I'll leave it as an exercise to the viewer to figure out how to extract that particular value. And then maybe if someone wanted to do a simulation study, you could repeatedly do this and see if you choose this one versus choosing this one, which one works better when you refit to train and calculate the test error, which one is a better representation of the actual error. And we know what that error is. It would be similar to this data, but that's something for a different day. Okay, so to recap though, this was where all the heavy lifting was done. So for each fold, we estimation, validation, split the data based on our predetermined folds that take it together, put all of the various validation sets in to be the whole data. Then we fit a model. Then we make predictions. Then we calculate our relevant metric. So to drive that home and to sort of eliminate some of the extra bits we did along the way, let's do this one more time. Let's do that Palmer Penguins data set. The data looks like this. Yeah. Wait, sorry. I need to do something real quick. I need to do, we'll call this best mod K and put it here. So when I send this code out, it'll still run. Okay, anyway. So I want to avoid dealing with any missing data. That's something for a later day when we get into analyses. So our data looks like this. Cool. So this is a classification problem. We want to predict the species here given, let's say, I don't know, bill length and flipper length or something like that. Okay. First, I got to test train split my data, and I'm going to steal some code for this, but we're going to sort of rewrite it. So we're splitting up the penguin data, and maybe what I'll do is I'll append this here so that it doesn't look, so it won't be confusing. Okay, so load the package, omit the missing data, test train split. Okay, so our training data looks like this. Cool. So now let's do 10-fold cross-validation. So from the caret package, I'm going to use this create folds function. I'm going to supply the response variable and we'll say k is 10. I should have stored that, but so here we see a vector for the observations that will go into the validation set for the first fold, for the second fold, all the way through the 10th fold. So we'll call this penguin CV indexes. Cool. So now, let's just say our goal is cross-validated accuracy for tree with I don't know, min split 2 and CP of 0.001. Some arbitrary model. So I'm just gonna do this once. I'm not gonna do it for all possible values. Okay. So let's do it once, then let's write a function, then let's get the results. So the first thing I need to do is get the estimation data, which will be the training data. Actually, let's do the validation data first. Subset to one of these indexes. So let's do the first one. And then the estimation would be the negative subsetting of that. Okay. Then the model is going to be our part, species. I need some variables here for features. What did I say? I wanted to use this one and this one. And as always, we fit to the estimation data. I'm going to need to, and then also, what did I say? I set some arbitrary values here, 0.001 and min split of 2. I've ran out of real estate, so we'll do something like that. Okay, great. So I fit my model. Now I need to make predictions. So let's do that. Predict mod validation. Oh, what? These are not predictions. These are probabilities. Type equals, oh gosh, class. Much better. Sorry, we'll say split. Say fit model. Say make predictions, and we'll say calculate metric, which I said was accuracy. So we want to look at, oh, I should store these. Okay, so prediction equal to in the validation data of the species, and I want that proportion. Ooh, a classic error. Did I not run this? I didn't. And I reused a variable name, and that's why I was in trouble. Okay, but anyway, so this is the thing we want to repeat for each fold. So now I write a function. So we'll say calc accuracy for a fold is a function of the validation indexes. And then it's a function that looks like this. So I'm going to take this, I'm going to put it inside of here, except I feel like I highlighted wrong, like this. All right, let's do this for a second. Okay. Except now this is what's going to go here and here. I think everything else is cool. So if I now sapply, oh gosh. What do I call it? Penguin. Oh, penguin. This. Okay, and then this function that I wrote. So basically what it's going to do is it's going to take each of these and pass it to the function, so it'll calculate with those things left out as the validation. We run that, and then if we wanted to get the cross-validated metric, there it is. Okay, cool. So in summary, get indexes within the training data that represent where the validation data is going to be for each fold. Then, for each fold, fit a model, make predictions, calculate your metric, repeat for each of the folds, average. Okay, done with my notes. So something you might be saying at the end of this nearly hour-long video now is, Dave, I know you're writing functions and not repeating yourself, but very clearly you're repeating yourself, right? Like, this function here looks incredibly similar to this function here. The only difference is, like, you know, you're not passing, you're writing bad functions that call into a different scope, but, you know, it's different data, it's different model types, and it's different ways predict operates and different metrics, but ultimately it's all very similar. Isn't there an easier way to do this? There is, and we're going there. Basically, different people have developed systems for doing machine learning in R, and one of the things that they all do is they have some way of doing this where you tell it, here's my training data, here's my model that I'm interested in, here's the possible values of the tuning parameters, and here's the metric that I'm interested in, and it'll just spit out a bunch of results for you. But for our purposes right now, in order to get you to prove to me that you understand what cross-validation does, I'm going to be having you do things like this in quizzes, and then in a couple of weeks we'll move on with our lives and be like, okay, we're just gonna use the systems and it'll make everything super easy. Okay, so wow, that was a long video. As always, if you made it to the end, good job, and I'll see you in the next one.